Good afternoon, everyone. Thank you very much for joining us this afternoon on our discussion with the science behind chelated minerals. Just as a brief introduction, my name is Kylie Mitchell. I'm a research scientist at Innophos, and my background's in inorganic chemistry, so really looking at the chemistry, the structure, even the biochemistry of these mineral-type compounds. So to get started, there's 3 questions that I want to make sure that I answer for you today. Those 3 questions are, why is mineral supplementation important? What is a chelated mineral? And also, how do you know if your minerals are chelated? So to dive right in, we're going to start with that first question of why is mineral supplementation important? I think we've all seen the news articles and the research reports that detail how the nutrient content in our food has decreased throughout the years. That is due to a variety of factors, whether it's processing, climate change, or what I'm showing you here, which is called soil dilution. Basically, we have more people on this earth than we ever have before, and so therefore we have more mouths to feed than any time before. But we have the same amount of land. So we have to increase our crop yields, but we have the same amount of nutrients in the soil, and so these nutrients get diluted throughout the different crops. Also, I think it's no secret that while we all strive to get a balanced diet, very few of us do. Actually, less than 15% of us actually achieve that balanced diet. So across the board, there's true nutrient deficiencies, especially in the area of these minerals, which are important micronutrients. As health-conscious consumers become aware of these deficiencies, they truly turn towards supplementation to fill these gaps. And for good reason. Minerals play an essential role in numerous bodily functions. We're all familiar with the benefits of calcium in bone health and teeth formation. Maybe less familiar to some might be selenium for its antioxidant properties. Chromium has some great insulin function properties. Iron's important for red blood cell formation and for reproduction. Zinc is great in immune function, and magnesium has a host of new and exciting research behind it in the areas of cognitive health, heart health, blood pressure regulation, nervous system function. Really, magnesium has a lot of new and exciting research and is a fantastic mineral to look into. But really, when we think about supplementing, consumers clearly understand the importance of these nutrient gaps and making sure to fill those gaps. And that's reflected in a healthy market growth for the minerals market. As you can see, it's growing at about 7% annually. If we break that down by mineral, we see that calcium still owns the market at 38%. But the really interesting one here is magnesium, which is growing at 14% annually, twice that of the market. And that's for a variety of reasons that I mentioned on the previous slide, in that there's a lot of new research surrounding magnesium. However, if we look at really the pulse of the market, this is another situation where I think we've all seen the news articles and the research reports that really focus in on bioavailability of supplements. This is what consumers are talking about. You even see articles that talk about, are these supplements just very expensive urine, right? So that's where we want to make sure that the products that we're supplying are bioavailable for the consumer and they can find the value in supplementing and getting those nutrient gaps fulfilled. That's where then we have to consider that, not all minerals are created equally. So if we think, okay, we're going to have a supplement and we want to include minerals in that supplement, magnesium would be a great candidate because of the fantastic growth rate that I showed, and because of all the fantastic health benefits it has as well. So we decide, okay, let's add magnesium to our formulation. The question then is what source, right? Are we going to use magnesium oxide that does have some good benefits, such as the high magnesium potency and the low cost, but also has some drawbacks in the inferior absorption and the metallic taste? Whereas something like magnesium bisglycinate, a chelated form of these minerals, brings a lot of benefits and could be what we use for our supplementation. Magnesium bisglycinate has increased bioavailability, greater stability, enhanced solubility, better digestibility so you don't have that nauseous feeling when taking these types of supplements, improved taste, and a positive safety profile. So this is where, if we're looking at adding magnesium to a formula, a chelated source of magnesium is really a good way to go. So when I keep saying this word, chelated minerals, for those that are unfamiliar in the audience, we want to answer the question just, what is a chelated mineral? So chelate comes from the Greek word chele, meaning claw. So then if we look at an illustration of how we form these chelated minerals, you start with your ligands, which in this case, I'm showing glycine here on the left. And if we look at this illustration of having these claw-like features to the glycine, then we have our mineral salt, magnesium oxide in this case. And then if we react those to form a chelated mineral, what we have is we can see, let me go on this side. We can see the nitrogen from glycine and the oxygen from glycine are really grabbing onto that magnesium like a claw on both sides of the magnesium. It's really, clipping on and grabbing on like a claw. And that helps create this protective shell. And this protective shell really has a stabilizing effect that brings about all of those benefits that we spoke about on the previous slide for these chelated minerals. Then the question becomes, okay, great, we want to add this to our formulation, but how do I know that the product that I'm getting is chelated? In this industry, a lot of these samples are white powders, right? So we look at the samples, sample A, sample B, and sample C, and they look identical. They look the same. So then we could say, okay, well, let's at least check the magnesium potency. Let's see if that can reveal to us the differences between these samples. If we check the magnesium potency, we can see that across the board, it's 11.7% magnesium. And that's typically what we see on the C of A, on the certificate of analysis. If you looked at sample A, you would look at the C of A, it would say 11.7% magnesium. Looked at sample C, same thing. You'd see 11.7%. So would we say, okay, well, these samples are the same. Then, we could just combine these, they're the same. But that's not always the case. And so if we use the illustration from the previous slide, what I'm showing you is that sample A might be our fully bound, our chelated source of magnesium glycinate with that nice protective shell around it. Sample B might be a 50% reacted material that has some fully reacted chelated material, but also some unreacted magnesium oxide and glycine. And then sample C might just be a dry blend of magnesium oxide and glycine at the right ratio to get you to 11.7% magnesium. So how would we know the difference between these three samples? That's when many in the industry turn to FTIR, or Fourier Transform Infrared Spectroscopy. However, though, this does not offer conclusive proof of chelation. I'm showing you the 3 FTIR spectra for those 3 samples on the previous slide. From just looking at these, would you know which one's chelated? It's a tough call. Would it be the top one because it looks different than the other 2? Which one is it? So if we reveal which one is the truly chelated, it is the middle one. That is sample A. However, if your supplier is using sample B as their standard FTIR, then if they're comparing for lot-to-lot analysis, they might just be making a consistent product, but it might not be the right product. And that's where we have to involve other techniques to show that we're actually making the right product that supports that FTIR spectrum, the middle one here, as sample A being the fully chelated product. So really at Innofloss, how we look at this is if you have 2 fingerprints, right? When you look at them from a distance, they look really similar. You could even argue they're the same. But only once you start doing some in-depth analysis, when you actually compare the fingerprint pattern, when you actually have some other fingerprints to look at side by side, can you start to see the differences between these. And so that's where we've developed a 3-step process to prove chelation. The first step in this process is called X-ray diffraction. This actually confirms the structure of the compound. Second, we do use Fourier Transform Infrared. It's a great technique, but it just needs to be applied properly. And then finally, we use thermogravimetric analysis, or TGA, to confirm the purity of the product. So if we walk through an example, if we look at our sample A, right, this is the one that we know is our fully bound, fully chelated material. The reason we know this is because we can look at the crystal structure, which I'm showing you over here on the left, where you can see this is not just a nice computer drawing. This is actual data that is generated from actually looking at the positions of the atoms. So what we can see here is that the magnesium sits in the middle, And then we can clearly see the oxygen of one glycine ligand and the nitrogen of another glycine ligand here. The oxygen and the nitrogen are actually coordinated to that magnesium ion. So they actually are clipped on and grabbing it like a claw. From there, we can then get a fingerprint that can help us identify when that situation is occurring. So that's what you're looking at on the right. This is called a powder X-ray diffraction pattern. So basically, it's like a fingerprint to show us that that represents the chelated structure. So the red data is showing you sample A, the fingerprint for sample A. The blue data is showing you the fingerprint for this chelated magnesium bisglycinate. And what you can see is for every point there's red data, there's blue data overlapping it. So these are indeed the same product, and sample A is fully chelated. So then you might say, well, what about sample B? Wouldn't that just show up to be the same thing? How do you know it's 50% reacted? XRD is pretty sensitive, so we can actually look into that and analyze it and see those differences. What you're seeing here is the fingerprint of sample B is shown in the red data. And then we want to identify what other what's called phases are present in the sample. So we can see there is some of the dark blue phase, which is the fully chelated magnesium bisglycinate, but there's also some other phases that are being detected, such as glycine and magnesium oxide. And you can see actually when we do a quantitative analysis that we get really close to the theoretical numbers, that XRD is sensitive enough to tell us, yeah, this is 50% reacted. It's not the fully reacted product. So then finally, if we look at sample C, we can see that it's just made up of magnesium oxide and glycine, and we can tell that from comparing the fingerprint of sample C, the red data, to the fingerprint of glycine and magnesium oxide. And again, they completely overlap, letting us know that we've identified all phases present in this compound. And you can see again that the theoretical numbers and then the actual numbers that we determine from the analysis are very close. And so this slide really shows you the power of XRD. So for any scientists in the audience, this slide might be of interest to you because I think this is truly a beautiful piece of data. What we did at Innophos is we took a lot of different samples, and we wanted to gather the data on all these different samples to see could we tell the difference between them. So we created a 50% reacted product, a 75% reacted product, 90%, 95%. These different samples we made so we could check them by XRD. What you can see is that the black data is the fully chelated magnesium bisglycinate. I'm showing you then a peak that's indicative of magnesium oxide. As you can see for the black data, it's completely flat in that region. Then we took our 95% reacted sample. So it's only 5% unreacted. And you can already, so this is the lime green data, and you can already start to see a peak right there. For the 90% reacted sample, the peak gets a little bit bigger. For the 75% reacted sample, gets even bigger. And you can see the trend here, that we can really detect even in tiny quantities if there's unreacted magnesium oxide or glycine present in these samples. So then finally, and we're not done there, we're not just using XRD, we're not just using FTIR. We want to have 3 pieces of data that support the chelation of our products. So finally, we use TGA. So this is looking at the thermal decomposition of these various samples, these various compounds. So sample A is the blue data, sample B is the green data, and sample C is the red data. And the first thing you can notice is they just all have different profiles, right? They all look very different. So again, this is sort of a fingerprint for this compound. I've also put glycine up on here in the dark red. And one key thing that you can see is that sample B, which does contain unreacted glycine, and sample C, which also contains unreacted glycine, both overlap in this region. However, sample A, which is the fully chelated magnesium bisglycinate, is flat throughout that region, indicating that we don't have any unreacted glycine present in the sample. So again, this is just another check for the purity of our compounds. So again, through this 3-step process, we are putting the data behind these products to fully prove chelation. Using the combination of X-ray diffraction, FTIR spectroscopy, and thermogravimetric analysis, we can use all 3 of these different fingerprints for comparison. So just to show you across the board what that looks like, if we have sample A, which is our fully bound, our reacted product, and again sample B on the bottom, which is our 50% reacted, we can compare the data for all three of these. We can look at the XRD, and those patterns are different for those two samples. We can look at the FTIR. Those patterns are different for those two samples. And then finally the TGA, and again we can see the difference. Only at this point would we then make the conclusion that the FTIR at the top of the screen, this one here, represents the fully chelated structure. So now we have additional data supporting that. So when we do a lot-to-lot comparison using that FTIR spectrum, we can be confident that it is the fully chelated product. So Innophos has carried out this three-step method for chelation on our ChelaMax chelated minerals product line. As you can see, we have 7 products in this line. We have 2 in the calcium family, 2 in magnesium, 2 in zinc, and 1 chromium. If there's time today, I'd be happy to answer any questions, but if there's not any time, I will be, or if we don't get to your question in this form, I will be at our booth at 2758 to answer questions. I'd be happy to talk about anything that we discussed here today in terms of the data and also about our ChelaMax product line. Thank you very much for your attention and your time, and if there is some time, I'll take any questions. So the question has to do with the absorption of the chelated minerals versus the absorption of, just our general oxide materials, like our magnesium oxides, zinc oxides. And this is, of course, one of the key questions in this area. When you look at the absorption of magnesium oxide, that's been shown to be as low as 30%. That's absorbed readily by the body. Then in terms of the chelated forms, those have been studied in a lot of different formats, so it's hard to put an exact number on the, if it's a twofold absorption increase, but across the board, those have been generally more well absorbed. Some numbers have been twice as well absorbed as the oxide form. So the absorption occurs in the small intestine. And so this is where there's a pH difference between our stomachs and the small intestine. In our stomachs, even the salts, they're soluble, right? They break apart just fine. But then as they pass to our small intestine and the pH goes back up to more of a neutral pH, they actually precipitate out and become insoluble. And so then this makes absorption very difficult. Whereas these chelated forms, because they have that protective shell around them, they can actually remain soluble in that environment and are therefore better absorbed. If I'm understanding your question correctly, so you're wondering about the difference between some of the glycinates that you're seeing, like magnesium glycinate or zinc, and then like the citrates. Is that your question? Okay. So in terms of comparative analysis, if you're looking for like an absorption number, that's a number that's really difficult to get at, and I haven't seen in the literature. But if you're talking about application benefits, that's where there's a lot of differences between them. Some might be taste, some might be solubility, because they will still have different physical properties to them. So depending on your formulation, that's where it might be advantageous to use one chelate versus a different chelate. The question is about the release of the chelate to then absorb the mineral. And so this is where with chelation, we can think of a lot of things like EDTA, right, that are great chelators and just latch onto these minerals and don't let go. But then that's not going to be helpful, right? Whereas something like glycine, citric acid, picolinate, they don't have binding constants that are so strong that they won't let go, but also not too weak that they don't stay intact. So it's a little bit of balancing something that chelates well, but not so tightly that it just never lets go. And so that's where then this, there's the action of kind of pulling that apart and breaking that down. Like you're saying, like that's a very difficult thing to follow in the body, right? You'd almost have to do isotopic labeling to see that. And there have been some of those studies in rat models. But the other point is then looking at the absorption in general to see if it's not released, then it won't get absorbed. Because there's been studies with phytate and EDTA where there's no increase in absorption by using those materials. So clearly it doesn't let go. Whereas with the glycinates, the citrates, there is increased absorption, so they have to let go at some point in that process.